So, predicting isomers drove me up the wall when I saw that this is one of the things we assessed, because Carey states pretty early in the beginning of the book that the only way to predict the number of isomers is to try them all. Sadly, math cannot help us in this case because it's just too complicated if you were to try to work it by hand. So I wish I could give you a great video saying, hey, given this compound, these are the number of different isomers you can come up with. The best thing I can do, and I can tell you this from having tried to write the test for it and saying, man, this must be all the answers, and come back next to like, oh no, I forgot about this, I forgot about this. This is hard to do, and it is so hard to do that it's really hard to kind of give you a procedure to follow through. So instead what I'm going to do is I'm going to give you some guidelines for kind of guessing what to do. Now, in terms of predicting isomers, we're looking both constitutional, we're looking more for constitutional isomers when we say that. Now, we can also be talking about stereoisomers. Easiest way to do that is count the number of chiral centers, and it's 2 to the n possibilities, but you gotta look for meso compounds, so go watch my videos on chirality. In this case, we're gonna stick strictly to constitutional isomers. So how do we predict the number of constitutional isomers? Well, what we wanna do is we wanna look at the formula itself. So let's say I give you C4H10 versus C4H8 versus C4H6. Each of these vary by 2 hydrogens. Now, a saturated alkane is going to have 2 times the number of carbons plus 2 hydrogens. So something like C4H10 is a saturated alkane. This makes it really easy. The only thing we can really change about this compound is how the carbons are connected, but there's no possibilities of rings or no possibility of rings or double bonds. So for something like C4H10, always start with your linear compounds, and then the only other option here is to move this carbon over. So there are 2 possible isomers of C4H10. In this case, the linear butane or the 2-methyl propane. Easy enough. When we get rid of hydrogens though, every 2 hydrogens we get rid of corresponds either to a double bond or a ring, and that's what makes this harder if we have unsaturated hydrocarbons. So again, start out with the linear chain. Now, because we're missing 2 hydrogens, we have the potential to form 1 ring, and so this is another option. Now, the nice thing about butane, or something with 4 carbons, we don't get a lot of possibilities. Now, in terms of all the different possibilities you can get for the linear, we know that we had 2 options for C4H10. We're deficient 2 hydrogens, so we've got to stick a double bond somewhere. Now, in the case of the branch, this is really easy. This gets a bit more complicated because we can stick the double bond here, or we can stick the double bonds on the end. And when we don't have terminal double bonds, we also have to consider the cis and the trans isomers. So, if you have 2 hydrogens missing based off the parent formula, you've either got 1 ring, which this will satisfy C4H8, or you've got a linear or branched alkane with a double bond. And with a double bond, unless it's a terminal double bond, you've also got the possibility of cis-trans isomers, or easy isomers. So basically, the groups being opposite each other across the double bond, or sort of forming this C shape. Gets even more compound when we get to something like C4H6. Oh, and even in making this video, fantastic thing, you can make another ring too. That right there. So you can make a 3-carbon ring, or the 4-carbon ring. Let's make it even harder. Let's get rid of 2 hydrogens. Now, if we have 2 hydrogens, we get rid of 2 pairs of hydrogens. Oh, I'm sorry, I didn't realize that was H6. It wasn't H6. So for the C4H6, we've gotten rid of 2 H2 groups now, which means we could form 2 rings, which is not likely in this case. You need at least 3 atoms to form a ring. So odds are this is going to be a ring with a double bond. We can also have 2 double bonds or a triple bond. How do we do it? This one's easy. We form a ring, and we've got to put a double bond somewhere. Now, we can also form a 3-membered ring. that will also satisfy the C4H6 formula. So when it comes to the rings, start with the smallest possibility, the 3-member ring, the 4-member ring, if you have enough carbons, 5-member ring, and so forth. Try not to give you problems that complicate it, but they do exist. What about the linear alkanes? Well, we had two possibilities from before. We had the straight linear, or we had the branch. Now, the reason we can't do this branch now is we got to put 2 double bonds on it, and it's just not possible. 2 double bonds would create basically a carbon with 5 bonds. Doesn't happen. So in the case of C4H8, we don't have the ability to put 2 double bonds in the branch. We could do this if it was C5. In terms of our linear chain, we have the choice of a triple bond or a double bond, and the triple or 2 double bonds. If we have a triple bond, we have the option of it being terminal or in the center. So for our alkyne, that's one possibility, and that's another possibility. For our 2 double bonds, we've only got one choice here, because if we put it in the center, we're going to have a carbon. Actually, no, we can do that. We also have another option, this nightmarishly high energy compound, where we have adjacent double bonds. So these are all the different conformation possibilities for C4, constitutional isomers for C4H6. As you can see, it's challenging. As you can see in this video, I even made mistakes doing it, and this was a video I prepped. So it is hard, but the best advice I can give you is just look at the parent alkane. If you could completely saturate that alkane, what would be your possibilities? As you get rid of hydrogens, you can either create a ring, a double bond, or if you get rid of enough hydrogens, triple bonds. With the rings, start with conformations that start with a 3-member ring, 4, 5, 6, and so forth. Every equivalent of hydrogen you lose, every H2 you lose, is a possibility for one more ring. So let's do a slightly harder example. C6H10, and I just want to do this to demonstrate to you the possibilities of the rings. We can create, we're missing 2 equivalents. So because we're missing 2 equivalents, we can have a ring plus a double bond, or 2 rings. For each ring, we have a 3-membered ring, or if we have 2 rings, we can have 2 3-membered rings connected. So 1, 2, 3, 4, 5, 6. This is the only possibility with 2 rings. This only has 3 carbons, so we have that option, that option, and that option. The rest are related by symmetry. And then we have to throw a double bond in there. So there's possibilities where the double bonds can go. They can go here, or within. In this case, we still have the same possibilities here, here, or here, or here. So 1, 2, 3, 4 possibilities, or 1, 2, 3, 4, 5, 6 possibilities here. There are a lot of possibilities. But again, as Carrie said it, you just got to go through and try all possible iterations. On my test, at least, I'm merciful, and I try to give you simple molecules where there's just a finite number of constitutional isomers that you can work through. But especially when you get to like large carbon chains, it is nearly impossible to find all the different conformations by hand. You just got to kind of work and feel kind of creative that day. So I'm sorry for this video, and I mean that sincerely. I'm sorry I cannot give you a procedure on how to find all the different constitutional isomers of a given compound. It's just hard to do, and you got to kind of brute force it and just recognize that every time you get rid of a hydrogen away from a saturated alkane, you introduce you start creating more carbon-carbon bonds within the compound, which creates a lot more possibilities for you.